Is my screen visible to everyone?
Yes, sir.
Okay, thank you. All right, so we are going to discuss about the Hilbert transform in some more detail today. So the idea here, very simply, is that if you've got a signal, um, if you've got a signal x of t and you look at its Fourier transform, it is always symmetric about 0 in the frequency domain. So if you are trying to use this as a density function, you don't make much progress because the mean frequency, which you think should be somewhere here, instead is here because it's symmetric. So you create another function out of this called the analytic function, which I can't draw here because it's complex. But the idea is that if you look at its Fourier transform, it is 0 on this side and twice on the other side. So it has the same energy as the original signal. It's just that it's packed on one side. Okay, and the analytic signal, because it's a complex signal, you can think of it as a complex number at each time, like so. At each time point, it's a complex number, so it has an amplitude and a phase. So this is called the instantaneous amplitude of xt, and this is the instantaneous phase of xt. Okay, and this thing may or may not be meaningful. Turns out, if it is a sinusoid, it is meaningful, and otherwise it may not be that meaningful. So, so just to give an example, if you did have a pure sinusoid like this, its Fourier transform will be a delta function sitting at whatever the frequency here is, omega naught and minus omega naught. But from this, if you look at the analytic signal, it is just that. Okay, so if this amplitude is A, this is A by 2 and this is A by 2. This is again A. So the analytic signal is actually just A e to the power j phi t. Okay, so it's a single delta function of magnitude A, and phi t there is omega t. So its instantaneous amplitude is fixed. It is everywhere. So if I plot AT, it's just going to be a constant A, and the phase phi t is just going to be omega t plus some initial phase if you want. So it's just going to change linearly. So if this is now the time axis, it is changing linearly between minus pi and pi, but the change is linear. So the derivative of the phase, which is the instantaneous frequency, is to be omega. Okay, so for a sinusoid, this technique works perfectly. In the previous class, I had shown you that. So suppose fs x is a sinusoid at 20 cycles per second at 20 hertz. So there you go. This is the Fourier transform of the original sinusoid x of t. So it is a peak at 20, but it has another peak at 980 or minus 20. So you compute the analytic signal, which is given by this formula here. And if I now look at the FFT of x, FFT of z, which is my analytic signal, it is now only concentrated at 20 hertz. This is wiped off, and it's twice in magnitude. So you can see that this is 1000 and the previous one is only 500. Okay, and now if I plot the amplitude or the absolute value of Z, it's flat at 1. See, it's barely changing. This is 1 point, so this is all just 1. So it's telling us correctly that the signal that you have has an amplitude of 1 at all times. This is the time axis here. And if I plot the angle of this, it's linear. Okay, so this is changing linearly, but only shown between minus pi and pi. Because if you add 2 pi, it doesn't do anything to the phase. And its derivative, I unwrap and plot the derivative here, diff. That is the instantaneous, that's the instantaneous angle. Okay, so you can see it's all fixed again about just one number. Let me normalize it properly. So I'll divide by 2 pi. So now it's 0.02, as you can see. But the diff, you have to, when you do delta t, you have to again, the denominator delta t is now 1 by fs. So you have to multiply this by fs to get the frequency in hertz. And as you can see that it's correctly telling you, excellent. Sorry, why it's correctly telling you that the instantaneous frequency is 20 everywhere, and the instantaneous amplitude is 1 everywhere. So it works beautifully for a sinusoid. Okay, so it's not guaranteed to work for other things, but for a sinusoid, it will work and work very well. Okay. Are you guys with me? Hello?
Yes, sir.
Yeah. Okay. This Hilbert transform is actually a very nice way to represent some signals in the time frequency domain. So suppose you had just a sinusoid and you said represent this signal as a function of time and frequency. Generate a time frequency power plot, and maybe there is some variation in the sinusoid. So Hilbert transform, at least the Hilbert-Huang transform, which I'm going to talk about next, was first used in studying waves. And if it's like thing where the amplitude might be just changing a little bit, and you represent that as well as you can, what you could do, compute the amplitude and instantaneous frequency, and then in the time frequency domain, just plot the amplitude at that frequency. So if you had a sinusoid, you'll get a very sharp line at exactly 20 hertz, or whatever the sinusoid is, and it's just going to be at 20. There's no spread or nothing. It's just a very tight, very sharp representation of sinusoid in the time frequency space. Okay, so if there is some variation, the instantaneous frequency just changes a little bit, suppose it becomes, or the amplitude changes a little bit, you will just see some variation around this, But essentially at each time point, there's just going to be one point. This is the time at which you are plotting instantaneous frequency. The amplitude is the color bar. So it will just be a scattered point here, and it will become just a straight line if it's a pure sinusoid. So this is a nice way to represent some type of signals in the time frequency domain. Okay. Now, obviously, the problem is what happens if it's just not just a sinusoid, right? Then you're stuck. So, for example, suppose I make a where you have two sinus. I generate a signal which is a sum of two sinusoids. 50 hertz. Okay. So I'll do this. Now let's look at the signal first. Plot X. Okay, so now this is how the signal looks like. It's maybe okay, we'll stick with it. It's a sum of two sinusoids. If I look at its FFT, now it has two peaks. Okay, at 20 and at 50. If I look at the Hilbert transform, again has two peaks, but nothing on the other side. So this is the analytic signal. So now what is the amplitude that it shows? Remember, now it can only give you one value of instantaneous amplitude and one instantaneous frequency. The signal actually has two instantaneous frequencies, right? So one at 20 and one at 50. Well, two frequencies. But the Hilbert transform can't really work that way. So now it's not going to give you anything intuitive. So if I just plot um, yeah, here I'll plot um, the instantaneous frequency, and see its instantaneous frequency is all over the place. In general, it is giving a value between 20 and 50. It's showing you something around 35, but all of a sudden it just changes in weird ways. So it's not very meaningful. You will have these dots, but you will also have a lot of other frequencies. Just because the signal has two frequencies, but at a given time, you can only report one frequency. Okay, likewise, if I plot the amplitude of instantaneous amplitude, the instantaneous amplitude is going back and forth like this, even though in the real signal, the amplitude is fixed for 20 and for 50. It's just that it has two sinusoids. So Hilbert transform by itself is unable to represent this. So what do we do in order to represent this properly in the time frequency domain? Remember what you expect, what you think you should. The ideal representation would be two lines, one at 20 and one at 50. But at a given time, you can only you're representing the analytic signal has only one instantaneous amplitude and one phase. So you can't have two dots like this unless you do something. What can you do in order to try to get to this signal of a representation? Again, this is a hard question. Try to think and let me know or guess something. So you've got a funky looking signal. I told you that the Hilbert transform representation sort of works only when the signals are more or less sinusoidal, have just one dominant frequency. So can I break this down into constituents, you know, as a sum of you know, signals that are more or less like sinusoids, and then compute the Hilbert transform. So that's the standard technique. What you do is you first pass this through a filter bank. So you will just have a bunch of band pass filters like this. So essentially, you decompose it into sinusoids. It's just that they're not perfect sinusoids because then, it turns into Fourier transform. They are approximate sinusoids by filtering through some band pass filter, which has some bandwidth, and then computing the Hilbert transform for each of these filtered signals. Okay, so then you will have one line for 20 and one for 50. In fact, for each time point, you will have as many instantaneous amplitudes and frequencies as there are filters that. Okay. So now, unfortunately, this method makes it very dependent on the type of filters that you are choosing, the bandwidth of those filters and the center frequency and all that. So it's not an ideal method that way, but nonetheless, it is a popular method, and this is another way of generating the time frequency spectrum, whereby you pre-filter the signal, essentially breaking it down into a bunch of sinusoidal-ish signals, and then computing the Hilbert transform on each of those components. Okay. So with that preview in mind, now I'm going to talk about the Hilbert-Huang transform. Is there any which is basically the same idea, but these sinusoidal-ish functions have some other slightly nicer properties that are not there if you just filter it this way. Okay, but the concept otherwise is exactly the same. So is this fine with everyone? Can I move to Hilbert-Huang transform, or are there any questions? You guys can still hear me, right?
Yes,
Yeah. Okay. Okay. So let's then talk about Hilbert-Huang transform. The idea is exactly the you've got a signal, LFP signal, so it has this dipole, and then oscillation and spike and whatever. And computing the instantaneous amplitude and instantaneous frequency to generate the time frequency spectrum is not meaningful in this case. It's only meaningful if you can decompose it into some sort of sinusoidal. However, there are some sinusoidal-ish signals that are not flat, whose frequency can change smoothly. Like for example, a chirp function. A chirp function is something that just becomes progressive faster. Okay, now this is something that you would call a sinusoidal-ish signal because it's just going back and forth. However, it's not a constant frequency. In a time domain, a chirp function looks like this. It's time and frequency. Okay, it will have a fixed amplitude, but it's going to keep increasing in frequency with time, becoming faster and faster. And this is actually a very common signal when birds tweet for, or you come across these kind of signals a lot of time. Um, so you want to be able to also have represent my signal, original signal here, this kind of function. These are nice functions. These are what you would call the sinusoidal-ish signal. And if you had a its instantaneous amplitude and frequency, you would get something like this. But if I give you frequency bands that are fixed, not fixed, so you need a more way to decompose my signal into constituent sinusoidal-ish signal. Remember, I am keep saying ish signal because it is sinusoidal in nature, but its center frequency is changing. So Hilbert-Huang transform is a method that allows us to do that. So it's a heuristic method. The mathematical details are not very. So it's a sort of practical algorithm-based approach. So I'm going to talk about that now. It's very in neuroscience, which is why I cover it here. So yeah, so all of this.
Sir, your audio is very choppy.
So able to see my screen again. Um, Folks, are you there?
Your voice is breaking a bit, but we can see the screen. It's all right.
Okay, okay. Uh, so disconnected. I was here before I connected. Did you guys see the screen and hear what I? This is just standard Hilbert transform. Okay. You signal and you get its instantaneous amplitude and instantaneous frequency. And now we are going to talk about Hilbert-Huang transform. Um, so let me just read this. One way to improve the time frequency resolution is to see instantaneous frequency at every time instant, which can be obtained from the Hilbert transform. It will always be meaningful if the signal has many frequency components. Think about filtering the signal in certain frequency bands. It's an approach that will work if the constituent um, sinusoids in the signal have the same frequency, but may not always work. For example, chirps in which the frequency keeps increasing. So another approach by Huang, and hence it's called the Hilbert transform. So the HHT, or the Hilbert-Huang transform, breaks the signal into components called intrinsic mode functions, or IMFs, which is like your sinusoidal-ish signal, but it is not obtained by just bandpass filtering the signal, but it is actually obtained in the time domain itself by looking at the maxima and minima of a signal and actually asking if the signal is going back and forth like this. So if you have got a signal, you are actually going to look at the maxima and minima and create an envelope out of it and sort of get rid of this mean component and eventually get to a signal which has a mean of 0 and a number of maxima and minima that are equal to each other. So these kind of functions are called intrinsic mode functions. And it's okay if it becomes faster also, as long as it has the same number of maxima and minima, it will qualify as an IMF. So Hilbert-Huang transform is a way to decompose a signal into what are called these intrinsic mode functions. And these mode IMFs can be very domain using the Hilbert transform. So the two-step function, one is called the empirical mode decomposition or EMD, which is a way to decompose the signal, use the Hilbert transform on the IMFs. That's your HT. I have to do the EMD, but that's it. This is it. There's nothing else beyond that. So let's talk about what IMFs are. So these IMFs are extracted directly from the signal and they say the following conditions. The number of extreme maxima and minima must be the same, must be equal to the number of zero crossings or differ by at most one. So this signal, for example, is an IMF. See that it's not a sinusoid, but the number of minima and maxima that it has here also is the same, and so is the zero crossings, the number of times that it crosses zero. If you count them, it will be the same. So that's condition number one. And condition number two is that the mean envelope value of the envelopes defined by the local maxima and minima must be zero at any point. So if I define the envelope like so, and this, the mean ought to be zero. If these two conditions are satisfied, this function is called an IMF. Okay. So if I give you a signal, how will you compute the IMF? So let's find that out. So it's as I said, not a theoretical approach. It's an algorithmic approach. What you do, so here's your one signal. It is in this case a wind speed. So what you do is you first find where the maxima, local maxima and minima, and then you generate these connecting functions called splines, get its upper envelope and the extrema can be simply be found by determining the change in size of the derivative sign of the time series. Then you compute um, the uh, envelope x up and x low using the lines, and then you compute the mean of that envelope. Mean is shown here, this black trace. And then what you do is you subtract the black trace from this original signal, get this. Okay, so remember that once I subtract this, by definition, that the envelope here will have a mean of 0, which is what you want for an IMF, because you just subtracted the envelope, the mean. However, subtraction could have produced now new local maxima which were hidden here. So now you start with these signal, repeat the procedure. You at the maxima and minima, and you keep doing this until these conditions get satisfied, and then whatever is left here is an I. Just an algorithm. You keep doing this till the resulting signal becomes an IMF. Satisfies the criteria of an intrinsic mode. So from this, I have produced one IMF here, and it's usually the most, the component that is most oscillating in the signal. So that's how you got one IMF. Then you just subtract that IMF from the signal and treat the residue as another time series and find the second IMF and keep doing this until the residue becomes really, really small. So eventually you will be able to decompose any time series as a sum of a bunch of IMFs plus some residue, which is very small. Okay, so algorithmically, it's very straightforward. So suppose I've got a signal here, which is a chirp function plus a triangular function. So this is the original signal. I do this and find this and I subtract it. And this is now an IMF because the maxima and minima are sort of, are same, and so are the zero crosses. And when I subtract this from this signal, I get second signal, and this is also an IMF, and the residue here is 0. So I have decomposed my signal into two IMFs. And notice that I am now able to deal with chirp functions also, which won't have a fixed frequency. That's the advantage of using HHT. It's decomposing it into signals that don't have to have the same frequency. So in the time frequency domain, now this triangular function will be a very low frequency component, and this thing will be a function like this. So you have actually represented your signal nicely in the time frequency domain.
Excuse me.
Yeah.
When we find local maxima and local minima, what is the duration of the signal that we found, or is it any duration?
Yeah, so local maxima and local minima are instantaneous things. So essentially, you're taking the derivative of the signal and checking when it's 0 and then when it changes sign. And based on that, you're going to find the local maxima and local minima. Okay, so it's just based on an algorithm here. The extrema can be found by determining the change of sign of the derivative of the time series. That's it.
I understand how that IMF1 came about, but like IMF2.
So IMF2 is just obtained by subtracting IMF1 from the signal. And in this case, once you subtract this chirp from this original signal, you will end up getting this. Now, if a real signal like a LFP signal here is not so straightforward, so you will keep getting these IMFs, and usually the first one is the the highest change in the signal, the highest frequency component. So you got this, you subtract it from this, and you got a residue. On that residue, you keep doing the same thing until you get another IMF, and you have to keep continuing. And eventually, the residue is going to be so small or so slowly drifting that you don't, you don't consider it, and the algorithm stops. Okay, but it's obtained by simply subtracting the previous IMF, so that eventually your signal is just a bunch of IMFs plus the residue. This residue is just going to keep becoming smaller and smaller. Does that answer the question?
Yes.
Yeah. So that's it. That's the Hilbert-Wang transform. You might, if you pick up any neuroscience paper, you will hear empirical mode decomposition. These are big sort of heavy duty words. But actually the idea is very straightforward. You want to decompose a signal into sinusoidal-ish functions or functions that are nicely represented on as instantaneous amplitude and instantaneous frequencies, like sinusoids or chirps. And the IMFs are like sinusoids with the provision that they're not necessarily flat on time frequency spectrum. They can be chirp-like functions also. And once you have these components, you can compute their Hilbert transform to get an instantaneous amplitude and instantaneous frequency and plot it in the time frequency spectrum. Okay, so now if I look at my original signal, this is our data, and I apply the Hilbert-Wang transform. So you see there are these bunch of traces, because for a given trial, these are the number of traces that you have are the number of IMFs that the algorithm has found. And for a single trial, the spectrum for given trial, slightly different instantaneous frequencies. So when you take the average, this is what you end up getting. This is the average of the 76 trial. And if you look at the change in power, now notice that it's able to capture the sinusoid, the gamma rhythm, and the transient fairly well. This is the comparison with wavelet transform, which captured this at higher frequencies, but then it sort of spread out here. And the gamma was also sort of spread out here. This is multi-taper, where you are representing the sinusoid, but not this. The Hilbert transform is sort of able to get both this and that. Not a foolproof method either. It has its own, limitations. But as you can see, it's not a filter bank approach per se. It's a different sort of philosophy, so to speak, of looking at the instantaneous amplitude and instantaneous frequency. But it's a different way of looking at the signal, and by not imposing the frequency components to be like this, which is what you would do in standard Hilbert transform, you are actually able to capture things like this also. Okay. So this is the Hilbert-Wang transform. Okay, so I'm done with HHT. Otherwise, I'm going to very briefly talk about another method or another sort of philosophy, very briefly, and move on. Okay. So, any questions on the HHT? So, in the homework assignment, you guys will be doing all of this. So you will get a taste of this. Yeah, Srishti, go ahead.
I have one doubt. Yeah. So the thing is that when you have one IMF, it has multiple frequency components again, right?
Yeah, but in a nice, smooth, always oscillating, this can't be an IMF.
Mm-hmm.
There is always zero. Until you get that, it's not an IMF. These are the two conditions for it to be an. So it's, and you can, see it's like a sinusoid in the sense that it will have a maxima and minima. The number of these will be the same, and it is mean of the envelope is zero. So a church sinusoid is an IMF, but anything that looks weird like this is not an IMF. So IMF don't have frequency component, but the frequency easily computed. It will have a meaningful Hilbert transform.
Okay. So we do not
Okay, and that is
extract.
why you decompose it this way. It's just that the
Okay.
Hilbert components won't be flat in the time frequency spectrum about a constant frequency, which is what you would do if you had filtered it first and then computed. It allows also for components that are smoothly varying in frequency over time, like a chirp function. Okay.
Okay, okay. So we are just getting like the change in frequency within the signal, what is happening.
In the IMF, yes. If the frequency changes smoothly, like a chirp function, it will still count it as an IMF, and then in the time frequency spectrum, it's just a smooth line with frequency, frequency increasing over time, like that. This could be an IMF. Okay.
Okay.
All right. So now let's talk about another class of representations. I'm just going to briefly touch upon this and again talk about this in an intuitive way. The toolbox that Journal of Neuroscience paper, which you guys should use for your homework assignment, actually is about the matching pursuit algorithm, which I'm going to talk about. Again, explained in a very sort of intuitive way, and that's what we are going to study. What's the big idea? That when you take the short wave transform, you can decompose the signal many ways depending on what your window size is. So you could choose a very short window and you can have these transient like functions. These are the basis functions that I had talked about earlier. Or you could have long functions, which are oscillatory functions. The extreme of this is actually just the sinusoids. This is the Fourier transform. Now you have no frequency time resolution, it's only frequency resolution. And actually the extreme here could be what is called a delta representation, where each basis function is just a delta function and a bunch of zeros otherwise. Okay, so this is now a range of STFTs, all of which, so any one of these set of functions can be used to represent your signal. Your signal can always be decomposed into a bunch of basis functions, which style your time frequency space. Like, so these are your signal can always be decomposed as a sum of the basis functions. Okay, this we had covered in the last class. The problem is that these tiles are bound by the this uncertainty principle, that the size of the tile cannot be, the area of the tile cannot be less than half, or if you look at this as the Rayleigh frequency, then each tile has an area of 1. So that's the limitation. So I can use one of these. But then I ask, hey, can I not use an algorithm which allows me to potentially use any one of these tiles from any of these representations? Okay, transient like tiles, sinusoidal tiles, and everything in between, Fourier like tiles, delta like tiles. Can I use all of these as potential basis functions to represent my signal? Okay, so the idea is that I'm going to basically make a dictionary or like take a big bag and put all these tiles, all of this plus all of this plus all of this plus all of this, and make a giant dictionary out of it. And say that, okay, my signal would be represented as a linear combination of any one of these tiles. So unlike the previous case where each of these set of tiles formed a complete representation, this is an over complete representation. You've got too many tiles. So the signal can be represented in potentially many infinitely different ways because you've got too many basis functions inside your dictionary. Okay, so this is an over complete dictionary now. And you just need a way to pick out which basis function to use. Okay, so matching pursuit algorithm is an algorithm that does that. I just have an algorithm which picks out from this huge massive dictionary one function which represents the signal very well. So this looks like a lot of complicated math, but it's actually very straightforward. So let's go through this very quickly. I say, okay, I start with my signal X, and I've got a basis functions inside my dictionary. This is a massive dictionary, a highly overcomplete dictionary, which means that the basis functions are not orthogonal to each other. They in fact are, highly overlapping. But I'm going to take an inner product with my signal. Don't worry about this Rn for now. I'm going to take an inner product with my signal with each of these basis functions. So I'm going to check how well is the signal looking like my basis function. The inner product is just how good the match is. And I'm going to do that for every single element in my dictionary and just pick out that the function that has the largest inner product. That's it. And I'm going to say, okay, my original signal is now represented as that basis function multiplied by whatever the inner product is, plus whatever is left behind, which I'm going to call the residue. Okay, so it's an iterative greedy procedure in which in each iteration, I just find the basis function, which I called an atom in this case. These are called atoms. They're just basis functions, nothing else. Which has the largest inner product with the signal. And then I subtract that part and treat the remainder as the new signal, and then find the atom that represents the maximum energy of that signal, and so on. So the math is complicated, but the representation in here is very straightforward. So let me show you this. I've got an original signal. This is my original LFP signal. I say, okay, let me do a very big search and find which tends to explain this signal very well, which means that the inner product of this signal with that basis function is the largest among all the basis functions that are there in my dictionary. So I search and search and search and find this. And I say, okay, this seems like a good function. Notice that this function is very well concentrated in frequency, but loosely concentrated in time. Okay, so this is a basis function which has good spectral resolution but poor time resolution. And I'm going to say, okay, my original signal, this green signal, is now what this blue signal plus whatever is left behind, which is the residue after one iteration. Okay. So this original green is just this blue plus the new green. Now I run the algorithm on the new green and say, okay, find me a function that best represents this signal, which means that has the highest inner product, and the algorithm finds me this atom 2. Notice that this atom is now very well localized in time, but poorly localized in frequency. Then I say, all right, my original green signal is now blue plus this red plus whatever is left behind, which is the residue after 2 iterations. And now when I do this, it may find an oscillatory atom like this, which is now, locked like this in the time frequency domain. Okay, and I keep doing this over and over again. So suppose I find 500 atoms, and it's going to give me a representation that looks like this. Notice that I haven't violated the time frequency uncertainty principle. Each tile has a minimum of area of 1. It's just that I'm no longer imposing a limitation that each tile is identical in shape, which for the short time Fourier transform. I'm now customizing my tiles depending on where the energy of the signal is. So if I have this 100 Hertz monitor refresh rate, it gets represented by a very sharp line. If there's a transient, it gets by a very transient like function. These transients are represented by these transient like functions. Okay. So now if I compare this to STFT or multi-tapering, notice that if it's a long window, I'm only going to get these. If it's a short window, I'm going to get those and those. Here it's sort of getting everything because of the way I'm doing this algorithm. Pretty neat, very cool. Not only that, if I've got 76 trials, when I average the 76 trials in ST and FT or MT, my tiles are exactly the same in each trial. They are not changing. So the only thing is what I'm going to do is average the value, this color for each of these 76 trials and get an average representation for that. That is how I'm going to get the average spectrogram for 76 trials. But I still have the same set of tiles in the time frequency domain when I'm using STFT or multi-tapering. Here, you'll get a different set of tiles. So when I average, I'm not only averaging the values, I'm also averaging out the tiles. Okay, so in a different trial, it will be slightly at a different place. So I'm no longer even limited to having the same set of tiles in the time frequency domain. So when I average this, I get a very awesome representation like this. See, the high frequency 100 Hertz refresh rate got captured so well. The transient got captured so nicely, which I'm only able to do to some extent when I use very short windows. But unlike the short time Fourier transform where I couldn't get the oscillations, here it's capturing the oscillation also so nicely. So this is the power of matching pursuit. Unlike your wavelets, which would just spill out like this, it still retains the, the shape here. And that's still a very transient like function. And it gives a time frequency representation. This is when I look at the change in power spectrum, which will far outperform any Fourier like representation. Okay, so I got the transients as well as the oscillations using the matching pursuit algorithm. Okay, so matching pursuit has its own limitations also. It's a greedy approach. So if you go and pick a wrong atom in one iteration, the remaining iterations are just wasted in trying to fix limitations. To represent signals that have both and oscillatory components, like our local field potential, turns out it is in most cases a very powerful algorithm. Okay. So that's all I'm going to talk about matching pursuit. There's a whole course offered on sparse signal processing by Chandramurthy in ECE department, where he will talk about basis pursuit and orthogonal matching pursuit and, you know, look ahead or orthogonal matching pursuit. And it's a class of techniques that employ these over complete representations. I can't talk about any of that in any detail here, but that's the general gist of this, that you start with a big dictionary of atoms. Okay, so here each one is an atom. So it's a very, very big dictionary. And you're trying to represent your signal as a linear combination of some elements of that dictionary. And if you say that, okay, I want to only have a few elements in the dictionary, so that's where the sparse part comes in. It's a very involved concept in itself, but the idea is the same, that you start out with a ton of functions, more than what you need to represent the signal, and only pick out a few that sort of represent the signal very well. And here we saw matching pursuit in action, and I hope that was clear to you. The math is more involved, so we are not going to deal with the math here. But I hope the intuition is clear to everyone. Okay, folks, so I'm done for today. We'll just have one more class on coherence analysis, and then we are done with the LFP analysis, and then we will start with EEG signals from Monday onwards. If there are any questions, I'll take them now, otherwise the class is over.
When we say that we can choose